Okay, hello. These are the problems for chapter 12 and 13 since they're the same thing, but yeah, they're just the same thing. So, I've got the problems here for these chapters. We'll start with this one. So, the slender rod of mass m and length L has a particle negligible radius mass 2m attached to its end. If the body is released from rest when in the position shown, determine its angular velocity as it passes the vertical position. So we need the angular velocity as it passes the vertical position, and so that's pretty easy, obviously. First, we can draw out some things that we need to know, right? So O is our origin, of course. We have an M here. The rod has a mass, right? So there's going to be an mg here. And this is specifically if we consider that the mass is uniformly distributed. This is going to be, if this is a quarter of the length, this is a quarter of the mass. So this is m over 4, mg over 4, right? And then that also means if we just take this to be our center here, this is 3mg over 4, right? And this is 2mg. Those are all our weights, right? Yeah, those are all of our weights. And then we can also consider that it's going to have this position when it's fully straight out, right? Here's our origin, of course, O. We're going to have, and then the ball at the end here. That means that the weight is just going to be like here, 3mg, because all the weight is going to be going straight down, like so, right? And then this is just going to be radius r, which is 3L over 4, right? And then, yeah, we're going to have, of course, a angular acceleration like this, omega, and then we're also going to have a velocity at the center of gravity, which is somewhere on this side of the rod. We're going to have a center of gravity which has a velocity going through it, v. And then that applies here as well. We're going to continue having our omega, and we're also going to have our v somewhere at the center of gravity. We're going to have v. I'll put an arrow and I'll put the v here. So now that we know those, right, we are going to be solving. So r, we need to get r somehow, right? And r is the length from O to the ball. So to get that, we have that r is equal to, well, the sum of mr over the sum of m, right? So that's pretty easy to solve for r. So the sum of mr is equal to, so we have one thing in this direction. We have a mass at the halfway point here, right? Which is m over 4. So we have m over 4 times its distance. It's at the halfway point, and it's to the left of the origin, so negative L over 8, right? Plus, then we have our next mass, 3m over 4. So 3m over 4 times our distance. That's at the halfway point of this, which is 3L over 8, right? And then finally we have our mass of 2m times our distance of 3L over 4. And this is supposed to be a capital L, right? And then we do the sum of m is equal to, so we have the rod has a mass m and the ball has a mass of 2m. So the sum of m is just equal to 3m, right? So as you can see, the m cancels with all of these. So when we do the division, so we're going to get that r is equal to, so this is a quarter. So this is negative L over 32 plus, let's see, 9 over 32. So negative 1 over 32 plus 9 over 32 is 8 over 32 plus, this is, so 8 over 32 plus 6 over 4. So that's 2 over 3 And then 8 over 32, divide by 4, so that's 2 over 16, so 1 over 8, and then we have 6 over 4. So, okay, I think I added that up wrong. But, oh, I think I did actually. Anyways, we're going to get 7L over 12 as our radius, which we are calling from the origin to this center of gravity here, right? I'll put a capital G for center of gravity. That's our radius R. And we need that to do the rest of the question. So to get our moment of inertia, right, we know that we have to use the moment of inertia equation for a slender rod. So if you were to look at moment of inertia formulas, right, you get these things. We have rod about center and then rod about end. We're looking at rod about center, which is half ml squared. So that's not a half, that's 1 over 12. 1 over 12 ml squared. Plus, we also have our other moment of inertia, which is the formula as we know it, mr squared. That's this one, right? mr squared. mr squared, like so. So I is equal to, so the mass of the slender rod does include, the masses are the same, by the way. It's the total mass in the question. So it's going to be 3m, so m is mass. So 3m over 12, so that's going to be 1 over 4 ml squared plus 3m 7l over 12 squared, right? And then adding these together, we get I is equal to, so this is a quarter ml squared. We're going to get L squared here. 49 over 144 times 3. We could take out an m as well, right? So that's going to give us 61 over 48 ml squared. And I will bracket off this fraction just to. So we now have the moment of inertia, and now we can finally solve for what we were looking for, which is the angular velocity as it passes the vertical position. So we're solving for this angular velocity. So, right, is released from rest, meaning that it has no initial kinetic energy. And if we consider the fact that if we make this our datum, there will also be no potential energy. So its initial energy is just 0, right? Now let's look at its kinetic energy here, right? So, I mean, its kinetic energy in its second state is only rotational, right? Because this is rotating. So that means we have a half I omega squared. And then we need our potential energy, which we have as mgh. And what's our h? Well, our h is, to the center of gravity, is r. So it's going to be negative r. So minus, and then the mass is 3mgr, like this, right? And then we can simplify this, right? We know that r is 7L over 12, so it's going to be 3 times 7, 21 over 12 mlg, like so. So putting these things together, we see, and we take this term as our L, and since it's a half, this 48 becomes 96, right? But that doesn't matter for now. We have like this, plug in our I to this, and then we can make this 96 as well, just to move this 2 over, right? So we have this. One of the L's cancel. The M's cancel. We have L omega squared minus 21 over 12 G. We know what G is. It is 9.81, right? But let's rearrange first. So we have 21 over 12. 21G over 12 is equal to 61 over 96 L omega squared. And we can just move this over, right? So we would get this is times 96 over 61. And then divide it all by L. Yeah, so divide through by L, and I'll just put the L here, and then take the square root of this entire term to give us omega, right? And we don't know what L is, so the only thing we can do now is simplify all our terms out to simplify the omega. So we'll have 21 times 96 over 12 times 61, and that simplifies to, let me see here, 21 times 96, and then 12 over 61. 96 over 12 is 8 or something. Yeah, it's 8. So that becomes 8 over 61, 21. It simplifies to 168 over 61 times G over L is equal to omega. And that is how you would solve that question. So yeah, as you can see, the question itself, there's a lot of little mistakes you could make, multiplying out, rearranging these things here, recognizing the initial energies, making sure your datum, I didn't actually draw it, but making sure your datum is this initial position, which gives you no kinetic energy at first and no potential energy at first, right? You need to recognize that you have your center of gravity at some arbitrary point here, right? And then you'd have to be able to solve for R at this point. And doing that is just this thing here. Because if you look at it, the M's cancel, right? Yeah. So this is an interesting question. I don't know if I would have been able to solve this if I got this on an exam, but I've showed it to you, so now you will be able to do it on an exam. So hooray for that. Right, guys? Okay. So question 2. Determine minimum speed v and the corresponding angle in order that the motorcycle may ride on the vertical wall like so. The effective coefficient of friction is 0.7. Note that the forces and acceleration lie in the plane of the figure, so the problem may be treated as one of translatory plane motion. Right? So let's get some free body diagrams and kinetic diagrams going. Remember what I said, first step is always a free body diagram. So we have something like this, the wall, and then the biker along the wall, right? We're going to call this our origin, O for origin, right? Now, we have something here. This is a force of friction, so that's a lowercase f. Force of friction, we have the normal force going out like this, and as you can see, this is at an angle theta, which is in correspondence with this angle theta, right? His center of gravity is here. We're going to reduce him to this, which means mg acts over here, and as you can see, it is in line with opposing the friction, right? And then, friction is equal to mu n, of course, right? And then now we can look at our kinetic diagram. Which way is he going to be accelerating? Well, if we have our g here, everything else stays the same, right? We know that he is accelerating in this direction. And I'm just going to put an A. Because that's his normal acceleration, is in this direction with r equals 10, right? This is normal acceleration. He has... And this is like a front view of it, right? This is the force of friction, and I should label these. This is the normal direction. This is the binormal direction, right? And then, so this is a view that doesn't include the tangential direction. Now we can consider a front view, right? Which does have the tangential. We have this, our origin. So this is if you were staring at the guy dead on, his friction, and then this is a tangential direction. So T for tangential, we'd have our normal out like this, which meets at this center of gravity G, which has some radius R. And then if we looked at the kinetic diagram, right, same origin, we'd have that yeah, we wouldn't really have anything. It would just look like this, right? So now let's get into actually solving. So we know that the sum of the forces in the binomial is equal to 0. So this is in the binomial direction, is equal to 0, which is equal to, we have friction, which is mu n minus mg, right? If we look at it, mg is here, center of gravity is here, but we can assume it's like, we can imagine that it travels to here and opposes the friction, which is mu n. So we have this relation, right? And we can solve for n is equal to, so we just add mg divided by mu. That's a b, not an n. N is equal to mg over mu, like so, right? Now we can look at the sum of the forces in the normal direction, right? And we know that those are equal to MAN. And let me just label normal MAN. And then this is equal to M. And then AN is V squared over rho. Rho in this case is R. So MV squared over R is equal to N, which is the only force here. And we know that N is mg over mu. So we get MV squared over R is equal to mg over mu. As you can see, the masses will cancel out, right? And then we can rearrange for our velocity. So V is equal to Rg over mu. I forgot a square root, Rg over mu. And now we can plug in numbers. So V is equal to, so square root of R is 10 times G 9.81 over mu, which is 0.7, like so. And calculating this, so we have square root of 10 times 9.81 over 0.7 gives us a velocity of 11.8 meters per second, right? So we've gotten that. And now we need to solve for the angle. So to do that, we can utilize the sum of the torques. So we're going to be looking at the torque now. And this was not actually drawn anywhere. I probably should have drawn it. But that's okay. So the sum of the torques is equal to I alpha, right? Which is equal to 0. The torques fully balance out. And then this is equal to, well, if we look at this, and we're taking our torques around the center of gravity, of course, right? We have this MAN, this force MAN here acting at a distance away. And we have the gravity acting at a distance away from, this is the moments around the origin. The torques around the origin, right? So we have some force MAN. We have some force of gravity, right? So we know that this is equal to mg sine theta minus MAN cosine theta. And the distance is this distance here, and I'm going to call this distance B. Right, so we'll put in a B there. But as you can see, since it's equal to 0, the B's cancel out, and the masses cancel out, like so. And we know that AN is V squared over R. So we get that V squared over R cosine theta is equal to G sine theta. And we can change this again to V squared G over R is equal to tan theta. And if we take the inverse tangent of this, we know V squared is 11.8 meters squared. G is 9.81, R is 10. So take the inverse tangent of that. We get a theta, which is equal to, let's see, inverse tangent of, so this squared times 9.81 divided by 10 gives us an angle of or sorry, this is supposed to be over GR. I miswrote that. So this gives us a theta of 55.0 degrees. And that is that question. So as you can see, I'd honestly say, at least in terms of my courses, this is a question that is harder than the exams. We didn't actually have like 3D stuff like at all. So we had no binormal forces or anything. We were just normal, tangential, and like torque. And that's all we used. But these are some good getting into 3D stuff so that you can learn this stuff better. Okay, next question. Here. The solid homogeneous cylinder weighs 300 pounds and is free to rotate about the horizontal axis 0 or 00. If the cylinder initially at rest is acted upon by the 100-pound force shown. 100-pound force right here. Calculate R of the force supported by each of the two symmetrically placed bearings when the 100-pound force is first applied. So what does that mean? Let's take a free body diagram and a kinetic diagram, of course, right? And this is a side view. Let me just side view, right? So we have our bearing like this. We have our center of gravity here, which I will denote as G, and it is some distance away from the ground, right? We have a weight mg acting on the block. We have some can I not move this? Okay, fine. We have some R acting on the center of gravity like this, which means we have components for R. And we know that this distance is 6 inches. We know that the distance, and sorry, R is not acting. R is not acting on the center of gravity. It is acting at some point O, like along the bearings, like this. This is R. There's 100 pounds down here, like so. 100 pound. We know that the distance from the top to O is 4. The distance from the center to the edge is 6. So, and we know that the entire thing is 12. So that means that the center of gravity, which we have taken to be the center, is at a distance of 6 from the whatchamacallit, from the bottom. So the center of gravity is 6 inches up, weight acts straight along it, right? And we have all our distances. And now for the kinetic diagram, still the same side view. We have from the center of gravity, force is acting in this direction, MA, like so, right? So now we can get into calculating this, and I need to separate this at Q3. So we have that the moment of inertia about the center of gravity, right, is equal to, so we have a quarter mr squared plus 1 over 12 mh squared, like so, right? And you can get those from here. So quarter mr squared is right here. Solid diameter, central diameter is this one. A quarter mr squared plus 1 over 12 ml squared. And I can actually make this image better and zoom in on it. We are looking at this solid cylinder central diameter, right? We're using this one. So that's where this comes from. And we're replacing L with H. So we want to get I, the moment of inertia about the origin, about OO, right? So to do that, we use parallel axis theorem. So IO is equal to IG plus MD squared. And this is the distance between the center of gravity and O, which, well, if this is a height 6, and this is also a height 6, and then this is 4 down, so the distance between them is going to be 2. That is our distance between them. Yeah. That is our distance between them. So now we can just plug in our numbers. So we have a quarter. Weight is 300 pounds. So it would be, so IO, and this is going to be extremely messy. So I'm going to try my best to keep this clean. So 0.25. So a quarter. M is 300 over 32.2. R squared is, we need to convert it to feet. So 6 inches to a feet is a half. So 0.5 squared. That's the first term. Plus, so 1 over 12. M is, again, 300 over 32.2. H is 12 inches changed to a foot, so 1 foot. So we can leave that. Plus, M, again, is 300 over 32.2. And then we can bracket this one up. This 1 over 12 should be bracketed up as well, like so. And then times d squared. So the distance is, as I already said, 2 inches. So that's change to feet is 2 inches to feet is, what is 2 inches to feet? To convert, divide by 12, so 2 over 12, 1 over 6. 1 over 6 feet. That is your equation for IO, right? And this is a long thing to put into your calculator. I'm just going to do that quickly, though. So 0.25, 300 over 32.2, 0.5 squared plus 1 over 12, 300 over 32.2 plus 300 over 32.2 times 1 over 6. And then that gives you a, this 1 over 6 is supposed to be squared, by the way. Squared, forgot to write that down. That gives you a moment of inertia about the origin of 1.62, 1.62 pound mass feet second squared. And that is a really messy, that's really messy. That's not where the dot goes. Dot, like so. Yeah. Pound mass feet second squared. So now we need to get our sum of torques. So we know that the sum of torques is equal to I alpha, because remember we're solving for the component of R. And, well, to do that, we need to get our alpha, right? Because we can do the forces in X, as you can see, to get the horizontal component. So we can do the forces in X. So let's do that. And we're calling this force F, by the way. And then this is equal to, so if we consider it, about O, the weight acts directly on it, R acts directly on it. So we just have this 100-pound force at a distance of 12 minus 4. So 8. At this distance of 8 inches away, which converted over to feet is 4 over 6, 2 over 3. 2 over 3 feet. Right? So, and we're taking this way to be our positive. So if you consider there's like a pencil trick you can use to figure out the direction, but this will be causing a clockwise rotation. So it's going to be a negative force, right? So we get that this is equal to negative F, and then the distance D. So rearranging for alpha, we get that alpha is equal to negative FD over I. So alpha is equal to negative 100 times 2 over 3 over 1.62. And then this is equal to, so 100 times 2 over 3 over this gives us a angular acceleration of negative 41.2 radians per second squared. And now finally we can solve for our r, right? And keep in mind that r is coming in from both sides. So there's 2r acting on it. It would be better to draw it out like this. This is also r, right? So we get that and we get that in the x direction, ma is equal to 2r minus f, right? And then, well, we can change a. We can change this into equal m d alpha, where d is the distance between O and G, right? So we already had that over here. So it's 1 over 6. So now to solve this for r, right, we're going to go r is equal to, so md alpha plus f, and then that's all over 2. So r is equal to, so m is 300 over 32.2 times d, which is 1 over 6, and then alpha, which is this, negative 41.2, negative 41.2. What just happened there? What? Negative 41.2. Oh, I know what that is. Plus 100 over 2. And then plugging this into your calculator, you're going to get that r is equal to, 300 over 32.2, 1 over 6, negative 41.2 plus 100, and then divide by 2. We get that r is equal to 18.0 pounds. And that is how you solve that one, right? Yeah, that was a long question, but it's okay. As you can see, these 3D ones are a lot more difficult and time consuming than the 2D ones for obvious reasons. But yeah, that's that question. On to the fourth question. Back to content. Oh, 3 more questions to go, right? And these are all 2D, so it makes things easier for us. Did the hard questions first, and now the easy questions. So, 50 kilogram crate rests on a horizontal surface. Coefficient of kinetic friction is 0.2. Determine acceleration if P equals 600 newtons. So, we start off with a free body diagram, like so. Free body, right? We have that, we have 600 going this way, 600 newtons. But I prefer to keep them in terms of their like variables. So we have P, we have N over here, and then we have the weight over here, and we have our friction force here. Now you're probably wondering, why is the normal force over here offset at a distance? Why is it not? Well, why is it not in the exact same place as the weight? Well, the reason for that is we have our center of gravity, right? G. So if, I've got an arrow for weight, but if the normal force was right in line with the center of gravity, right? We would have tipping, because our moment would be this force. So we'd have a torque from this force, and we have a torque from the friction. And since this force is it's kinetic friction, so that means that the force is obviously causing movement, right? So if it's causing movement, and the friction just counters it a little, but that would cause this to tip like so, right? But we know that it's not going to tip, which is why the normal force is offset by some distance here, right? We need to get this distance, of course. And then obviously the kinetic diagram is just like this, MA. That's our kinetic diagram. So anyways, yeah. So keep that in mind for your questions. If your thing is not tipping, your normal force is going to be offset because it needs to counteract any other torques and moments that are created, right? If it was in line with G, then the normal force would cause no torque, it would cause no moment, and then that would make a sum of the moments that does not equal 0, right? So keep that in mind. Anyways, to actually solve the question, we can look at the forces in X. So we have MA in X is equal to, we have, so P, which is 600, minus mu N. And this is mu K. And then this is in our, this is in our X direction. In our Y direction, we have a 0 is equal to N minus mg. Therefore, N equals mg, right? This is easy. We can plug in N equals mg into the X equation. So going back to X, we have MA is equal to 600 minus mu mg. And now we can solve for A just by dividing everything by M. So A is equal to 600 over M. So mass of 50. So 600 over 50 is 600 over 50 is just is 12. Minus mu is 0.2 times G 9.8. So 0.2 times 9.81. So minus 1.1. Minus 1.962. A is equal to, so 12 minus this. We get our acceleration is equal to 10.0 meters per second squared. And that's it, right? That is that's how we get our acceleration. But I'm going to add on a bonus calculation because, as you can see, we have an offset here, right, that prevents tipping. So how would you go about calculating this offset? Well, you use the fact that no tipping occurs. So that means the sum of the torque is equal to 0. And now we're doing a torque analysis here, right? So 0 is equal to, and now let's just consider, we're going to take counterclockwise to be positive, right? So let's look at this. If we use P, it's going to cause a clockwise rotation. So we have 600, and it is here, 0.8 from the ground, 0.2 from the top. That means, and the center of gravity is at the halfway point, 0.5. So we have a distance of 0.5 here, or 0.8 here. So we have a distance of 600 times 0.3 for the distance. And then let's look at the force of friction is also going to be causing a clockwise rotation, right? Because if you consider it, it's going to be going like this from the force. And then this one is going to be going like this from the force, right? So it's minus mu n, and then this distance is 0.5. And then now our normal force, well, let's look at it. If it's going up this way, it's going to cause a rotation like this, which is clockwise. So plus nx, and it's at some offset distance x, right? This is all equal to 0. Now we know what n is, we know what mu is, and we're solving for x. So x is going to be equal to, so we have, we add these two, so these become positive, and then divide by n. So we have 600 times 0.3 plus mu 0.5. This is over n. N was mg, so this is over mg, like so, right? And then mu is just mu, right? So solving this, plugging in all our variables. So 600 times 0.3 divided by 50 times 9.81 plus 0.2 times 0.05, times 0.5 gets us a, a distance of 0.467 meters, right? Yeah, N is mg, so yeah, that makes sense. Yeah. That's what happened. That's the distance that you need away from the, this is the horizontal distance away from the center of gravity. You need to stop it from tipping, right? Because if it was to tip, it would not follow it wouldn't follow proper stuff. Anyways, onto Q5, right? This one. At the instant shown in this 20 kilogram cylinder rod has an angular velocity of omega equals 5 radians per second. Determine angular acceleration and horizontal and vertical components of reaction of the pin on the rod at this instant. So we're going to start obviously with free body diagram and kinetic diagram. We have our rod like so. Now, if you know anything about pins, right, and we have our center of gravity here, mg, or the weight, whatever, we have a moment like so, which is 60 Newton meters. We have our angular acceleration omega, and then we have an ry and an rx. Ry, and R stands for reaction force, and Rx, like so, right? And then now we look at our kinetic diagram. We're going to have, so MAT, MAN, and we're going to have our I alpha for the torque. That's kind of messy, right? You should know about pins from statics and like what the reaction forces for pins are, right? They stop movement in the X and Y. And then if you have a wall, it stops moments, moments. Never mind, you don't need to know that. That's whatever. That's from statics. You should know that from statics. Anyways, now we're going to do our force analysis. So in the tangential direction, right? In the tangential, we have that we have Ry minus mg is equal to negative MAT, right? But what do we know about AT from the formula sheet? AT is equal to alpha R. And R is just the distance, which is 1.5. So we're going to rewrite this as alpha 1.5, right? And then now we look at the sum in the normal. We have that Rx is equal to negative MAN. And we know that MAN is from this omega squared R. So omega squared 5 squared, that's not squared, 5 squared, and then R 1.5, right? And we know what the mass is, so we can solve for Rx. The mass is just, the mass is 20, so negative 20 times 25 times 1.5, and that gives you an answer of Rx is equal to negative 750 newtons, right? And that's our Rx. Rx. Now we still need to get Ry and the angular acceleration, right? So to do that, let's look at our sum of the, and also I forgot to, this is positive, like this. I forgot to mention that. Anyways, the sum of the torques, so we have negative, and this is now torque analysis, so negative I alpha is equal to, we have our 60, negative 60 And then let's look at what this mg causes in terms of rotation. It will make it rotate clockwise, so negatively, minus mg 1.5. And then we know what mg is, right? But keep in mind that this is the inertia about O, and we don't know what that is. So we need to change this into the inertia using parallel axis theorem. So we'll have negative out front, Ig plus md squared is equal to negative 60 minus mg 1.5. So negative 60 plus m 20 times 9.81. D is 1.5. I mean, times 1.5. Wrong thing. So this is negative 354, like so. Anyways, as you can see, the negatives cancel. So Ig is the one for a rod. So if we look back here, 1 over 12 ml squared, right, where L is 3. So 1 over 12, 20 times 3, 20 times 9. 1 over 12 times 20 times 9, so that's 15 plus 20 times 1.5 squared plus 20 times 1.5 squared gives us 60, right? Times an alpha. So we have 60 alpha is equal to this. And then we take this number and we divide to give us our alpha. Alpha is equal to 5.91 radians per second squared. Now we have alpha, and that means we can go all the way back to our tangential and solve for Ry. So back to tangential, we get that Ry is equal to mg minus m alpha 1.5. Plugging in our numbers, mg is 20 times 9.81. M alpha, so 20 times 5.91 times 1.5. We get an Ry that is equal to, into the calculator, 19.1 newtons, right? Now, a question here that you might have is, instead of taking our moments around O, could we have taken our moments around G? Yeah, we could have, right? It would just make it that Ry exerts a moment instead of mg, right? So, or whatever, torque, whatever you want to call it, right? So then we'd have two equations and two unknowns. Like we'd have alpha and Ry in both equations, so you just have to do some substitution. And that's all that changes that. Anyways, on to the final question. Right here. The 100 kilogram cylinder rolls without slipping. What is that blue stuff? Whatever. Rolls without slipping on the horizontal plane. Determine acceleration and angular acceleration. So, as always, free body and kinetic diagram. Remember, it's rolling without slipping, so keep that in mind. Anyways, here we go. We have a center of gravity. On it, we get mg. Acting up from the ground, we have the normal force. Acting like so, we have 200 newtons. And then we have a friction force opposing the motion. And then in terms of the kinetic, we have ma and I alpha. Just like that. And of course, let's set up our, don't curve. Let's set up our positive like so. There we go. So there's our free body diagram and our positives in turn. So for f of x, in the x direction, right, we have that it's equal to ma. So ma is equal to 200 minus friction, right? And I should say this is in the x direction, right? But we can change this into 200, or sorry, m alpha r is equal to 200 minus f, right? From this relation here, a is equal to alpha r. So now we can look at it in the y direction. There is a perfect balance, so there's no upwards acceleration, no downwards acceleration, no angled acceleration. There's angular acceleration though. Okay, I apologize. So we get n equals mg, which is equal to m is 100, g is 9.81, so 981 newtons is what n is equal to. And then finally we can do our torque analysis, which is I alpha is equal to, we have and we're taking our torque about the center. So as you can see, only friction causes a torque. So we have Fr. So we have two equations, two unknowns, right? Where we don't know what alpha is and we don't know what F is. So we can very easily substitute that F is equal to I alpha over R, right? And then I, in this case, if we look here, I will be, we have a disk, so it's half mr squared, right? So it's equal to a half mr squared alpha over r. So one of the r's cancel. So it's a half mr, right? Half mr alpha, where m is 100. So we can plug this into our x equation now. So we have that ma is equal to 200 minus a half mr alpha, right? And we're solving for alpha, right? So we get that alpha is equal to, so we'd have, swap these around. So 200 minus ma, and then multiply this by 2, divide by mr over mr, like so. So yeah, that would be like that. Okay, and then so this gives us a alpha which is equal to, so 200 minus ma. M is, what is m? Oh wait, sorry, this is not this is supposed to be alpha r. So okay, m alpha r. I read the wrong equation, so this rearrangement is wrong. So we're gonna put the these terms on the same side. So m alpha r plus a half m alpha r is equal to 200. And we can take out an alpha r. Alpha r is going to be m plus m over 2. So this is just 1.5 m, right? Is equal to 200. And now we get that alpha is equal to 200 over 1.5 r, right? And r is 0.3. So we get 200 divided by 1.5 times 0.3, which gives us a which gives us a angular acceleration of 4.44 radians per second squared. And then multiply 4.44 times radius 0.3 gives us a acceleration of 1.33 meters per second squared, right? Because we know that a is equal to alpha r. So that is how you would solve. Oh, I forgot the m. Sorry, this is 1.5 m. M is 100, right? So 1.5 times 100 times 0.3, also known as 1.5 times 30, and then 200 divided by that is 4.44, and then multiplied by 0.3 gives you 1.33. So those are all the questions for chapter 12 and 13 combined into one. Yeah. So there's going to be one more question video after this. Whatever, that's nothing. So thank you for watching. I hope you learned something, and bye.